All right. Let me share my screen. Give me a second. 301 IQ. So let's start by reading this question. If you notice, this is going to be the exact same question as 300 IQ, which is what we just covered, except the constraints, where there's going to be 100,000 players, and S is going to be between 1 and 100,000, which means that we can't really do like a n squared algorithm, for example, as Victor did. We can't, like, we have to do something more of n log n type things, because remember, as Victor said, we should try keeping our total number of operations below 100 million, and an n squared operation is just going to be too big. So let's take a look on what we can do. So first of all, okay, let me make a new thing over here. We can use prefix sums just as Victor uses. So, but I'm going to use it in a slightly different way. So let's take a look at this. Let's take a look at this example. So let me just delete this. Go on. Let's use a pen. So let's start with this test case over here. So we have 5 things. First person gets 5-1, then 4-2, then 5-3, then 1-3, then 2-1. And like the first details of this method I'm doing is like similar to what Victor does. It's not exactly the same. I'm going to be working with 1D prefix sums instead of 2D. But if you want to, but this also works with the very first question as well. So anyways, what I'm going to do first is sort this list out. But first by the score on the first test, then by the score on the second test. So this would be 1, 3, 2, 1, 4, 2, 5, 1, then 5, 3. So what this does is basically now we know like who got the lowest, and then so on and so forth. So we know that basically like 1, 3, since it's at the very bottom, it can't pair with anything above it. 2, 1, it could pair with everything above it, but it can't pair with 1, 3. It doesn't work. And then 4, 2, you can see if it pairs with these two, but it turns out it can't. And then so on and so forth. So basically what happens is we can create a prefix sum just as Victor did. So based upon the value of the things on the second row. So if we look at on the second test, not the second row, my bad. So if we look at the possible scores in the second test, there's 1, 2, and 3, right? So we can start iterating to the very first person we have here after we've sorted. So if we start with this person, 1, 3, there's no one above him. So he's not really better than anyone. If we look at 2, 1, and okay, wait, before that, after that, we can add 3 over here, right? We can add like a 1 over here in this prefix sum. So basically what happens is that, this prefix sum would look like 0, 0, 1. This is the value themselves, and this is the prefix sums. And what these values represent is that it's going to, like, the value for 1 will represent how many people got 1 in the second test that we've iterated through. Like, the number of people we've iterated through so far that gotten 1 on the second test. The 2 represents the number of people we've iterated so far that got 2 on the second test. 3, the number of people we've iterated so far that have a 3 on the second test. And this is just the prefix sum, which is as Victor described earlier. So for 2, okay, so once we iterate through this, right, we're at 2, 1. And we already know that like 2 has a higher score in the first test than 1, right? So we just need to compare how many have a lower score than this guy on the second test. But of course that's 0 because he got a 1 on the second test. As you can see, it has to be strictly greater. So like the prefix sum for when there's 0 is like simply anyone either. But what we can do is actually we can replace this 0 with a 1, which means that this prefix sum would become 1, 1, and 2. So we finished going through that. And now we're at 4, 2, right? So when we're at 4, 2, we know that, again, this first test 4 is going to be greater than the first test of the people we previously iterated through. And in the second test, we can just look at these prefix sums. So we know the prefix sum of like the number of people who scored up to a 1 on the second test is just 1. So this guy would be greater than 1 person before him. And now we iterate through him. So then we add a 1 over here. So the new prefix sum is just 1, 2, 3. And then we keep iterating. So this 5, 1 guy, for example, we would, because the second test is only a 1, it's 0 because it's not greater than anyone else's. So our total is still just 1. But the thing is, we don't add a 1 here right now. We have to wait until we go through all the people who got a 5 on the first test, because otherwise we count 5-3 as being greater than 5-1. But that's not true, because remember in the question it says it has to be strictly higher than the other player on both IQ tests, which means that we would just look at 5-1, realize it's not greater than anyone, look at 5-3, realize he's greater than these people. He's greater than this amount of people with a 2 or less. So there's 2 that he's greater than. And then later we would add 1 to the 1 index over here and 1 to the 3 index over here. So that's the basic gist of the solution. But if you notice, this is also going to be an n squared solution, O of n squared solution, which is not good. We don't want O of n squared, we want O of n log n at least. So this is bad. But there is something we can use to make this from O of n squared to O of n log n. It's actually a data structure that's it's not too complicated, but it's beyond the scope of work we're going to teach today. We're just going to black box it. But I'll tell you what it does. I'll tell you what it does, not the specific inner workings, but how it's used. So basically we're going to be using something called the BIT, the binary index tree, also known as the Fenwick tree. Those two are the same thing. So what this does is that it can update an element in O of log n. So let me just type this. Update O of log n. And then it can also find a prefix sum in O of log n. So this is basically what it does. So for example, let's say we've iterated through these guys so far, right? And then when we want to look at this guy, we can find the prefix sum in O of log n. And then after that, we just update one position. That's also O of log n. So basically, you just do that O of log n operation n times, and suddenly it's O of n log n, which is what we want. And by the way, I will be posting resources for to teach what specifically a BIT does on our YouTube channel in our description. So, but right now we're just gonna black box this. So let's start coding up what I explained earlier. So as you can see, this is just a BIT. What happens is this is just like a black boxed code. My bad. What this does is basically this just creates a BIT. This just adds a specific number to a specific index of the array /BIT. And what this does, it just finds the prefix sum up to that specific index for the BIT. So let's start coding this up. So first of all, we note that there's going to be there could be up to 100,000 lines because n is 100,000. So let's just create a buffered reader instead of just using scanner. So buffered reader input equals new buffered reader new input stream reader system.in. Boom. Then let's just input n. So it's just an integer to a parsed int input.read line. So this is how we get n. Then after that we do then what's next? So we can create a for loop here, right? That can take in every single thing over here. But if you think about it, maybe doing this already is not the move. What's better to do is first of all we have to look at how we're gonna solve this. So what we start doing to solve it is by sorting all of these. But how do we sort pairs? That's the thing. We have to create a new class with a comparator so that we can sort it. So let me just do that real quick. So status class pair implements comparable pair. So what this basically is I'm making each student a pair. So then it's attached to its 2 IQ scores, A and B, and then I'm creating a comparator that can compare each pair. So this can sort the pairs like this, how I want it to. So in A and B, let's just implement. We're just initializing a pair. This is just like how to initialize a pair, and then this is compared to boom if a greater than p dot a return 1, if a less than p dot 1, if b greater than p dot b return 1, and then return -1. So yeah, what this does is basically creates a pair with the 2 IQ scores of a student, and then we can sort it using this structure. So basically, let's create the pair right now of each person's IQ. So pairs IQs equals new pair n, because there's going to be n students. And also one thing to note that for the BIT, we're going to make it of a specific size, right? So if we want to like limit the, actually, this doesn't really matter, but it's just something that like I like to do, just to like conserve a little bit of space. So I'm going to create something called bmax equals 0. So what this does is when we're inputting every single second test score here, we look for the maximum test score, because that's going to be the number of elements in the BIT array. Because again, we have, as you can see, like 1, 2, 3 over here, and that's just going to be the maximum. That's going to be the maximum number of elements. So we can just use that when initializing the tree. So let me just show y'all. So let's just first create a string tokenizer. T equals new string tokenizer. Input dot read line. This is just again inputting everything. A equals integer dot parse int. B equals integer dot parse int sb dot next token. And over here we just do it if b is greater than bmax equals b. So this is going to be the greatest second score, as you can see here. Then we just initialize these pairs. So it's just new pair a b like this. Now what? So first of all, we already created the pair array, so we can just sort that, because that's what we want to do before like actually iterating through every single pair. Of course, we need to sort it. Then before iterating through every single pair, we also need to create a BIT. So we can like store the prefix sum and store like, yeah, you get my gist. Equals new BIT. The total, since the maximum B value is Bmax, we're gonna put Bmax plus 1 as the size. And then long ret equals 0. So what ret does is basically it's just going to be what we print out. It's going to be the number of pairs of students, such that like one student like majorizes a second. And by the way, we're making it long because, as you can see here, the answer might not fit in a 32-bit integer. So let's just keep it as a long. So now let's start. So first of all, let's just do this. So what we're going to do in this for loop is iterate through every single element of this array. So as you can see, is what we did here. Start with 1, 3, 2, 1, 4, 2, 5, 1, 5, 3. So we just iterate through all of those. And actually, another thing I'm going to do is I'm going to create an array list because we need another array list to kind of store the second, like in case things are equal. What I'm saying is that let's say we go through some array of pairs, right? So we go through 1, 3, 2, 1, 4, 2. Then we're at 5, 1, and 5, 3. But if we go through 5, 1, and then right after that we add like 1 to the 1 position over here, then it's gonna say our algorithm will tell us that 5, 3 does majorize 5, 1. And the thing is, that's not the case, which means that we have to add like the 1 and the 3. We have to add like 1 to the 1 index and the 3 index of this counting array, I'd say, of this like BIT counting array, after we iterate through all the ones with the first test value of 5. So basically we just iterate through all of these, and then we add the values to the BIT. So basically, I'm going to create first of all a variable cur a. So what this does, it just like shows our current a value. So like if our a value, as in like the first test value we're currently on. So like 1, 2, 4, 5, 5. And if our a value of like the current pair we're looking at is greater than the A value of the previous pair, we know we can just add, like, we can just update the BIT with all the previous values second test scores. So then we can make another array list integer, add equals new array list integer. So this is just going to contain all the previous test scores. So, like, for example, after we go through these two elements, add would contain 1 and 3. So let's start with this for loop. So basically what we would do each time is we would first of all add this value to the add array list, right? So what this does, actually this is like a really bad notation, but it's whatever. What we do is just we add, like, so let's say we're on 5-1, then we would add 1 to this array list add, which would later add to the BIT later. So then what else we do is we're going to take this value, right? Because when we iterate, we're trying to find the number of other elements that each person, that number of other people before them that each person majorizes. So what we can just do is like plus equals. Now we can just use the BIT to just query the prefix sum of the first I elements. So we can just query IQs I.B minus 1. So what this does is it just finds a prefix sum of like everything before it. So if we're like at 5-3, it would find the prefix sum of up to 2. Then before that, we can do this. Basically what this does is if let's say like the element we're at now, right, is greater than the cur A. So let's say if we have an element like 7-4, then we realize it's greater than the cur 7 is greater than the cur A, which is 5. Then we want to update the BIT with all the new values. So we would have to update it with all the values of an add. So basically we take this tree, which is the BIT, and then we add this. Basically what this does is just adds a value of 1 into the position that's represented by whatever B values currently in the array, whatever B values are in the array list, and we'll just keep doing this. And we just remove this value. So then after we go through this while loop, the array list is empty again, and we can just like repeat that over and over again. And then finally, we have to update the new current A, because again, since IQ's I.A is greater than the current A, we need to update that because it's the current A we're looking at. So I think now we're pretty much done because, yeah, we've gone through our whole for loop, our whole process of iteration here, and we've covered all the bases. So we can just print out the answer here since we already added everything here, and let's see if it works. And there's a compilation error, so let me take a look at it for a second. Let's see where I screwed up, guys.
Oh, by the way, you can just click run code instead of submit code to test it.
Oh, okay, let me see. So it says while add.size is greater than 0. Oh, shoot, I did not put that. Thanks. Now let's see if running the code works, and it works, so let's try submitting it. All right, so as you can see, it's all accepted. So does anyone have any questions about this? All right, I'm assuming there's no questions, so let's move on to problem 4.